Welcome back to Acids and Bases and Salts. In part 5 of this unit, we're going to be talking about polyprotic acids. That is, acids that have more than one proton or more than one hydrogen. Let's get started. So polyprotic acids can donate more than one hydrogen. This should say H plus with a superscript in a solution, but they will lose the protons only one at a time. So if a polyprotic acid is a strong acid, it will be strong for the first dissociation step only. Subsequent dissociations will be weak, and there is a different Ka value for each possible dissociation. Let's start by looking at that Ka chart on the back of your notes. I see a polyprotic acid, H2S. There are two protons in that H2S, and so its conjugate is HS minus. But then I also see, further down on the list, HS minus, which can turn into S minus 2. So I've got an acid that will dissociate one proton at a time from H2S to HS minus, from HS minus to S minus 2. Notice that there's a couple of those on here. There's an H3PO4, an H2PO4 minus, and an HPO4 minus 2. So each of these are going to lose one at a time. So let's see how this works in context with problem number 12 on your notes. This question is asking to write the two reactions for the dissociation of H2CO3 and then which acid is stronger. So H2CO3 we know is an acid, and if you reacted it with water, that acid would give a hydrogen to water, which means water would turn into H3O+. But the thing is, it's only going to give one hydrogen to water. So if you take H2CO3, take away an H, you're left with HCO3, and it's now negative because it's lost that positive proton. So the second reaction starts with that HCO3, which is also an acid. It also starts with H. It will also donate a hydrogen, which means it's going to make another H3O+, but what will be left will be CO3 minus 2. So if we go back to the Ka and Kb chart that we were just looking at, for H2CO3, it's in the acid column, it's carbonic acid, and its Ka is equal to 4.2 times 10 to the negative 7. But if you look on the chart for HCO3 minus, its Ka is 4.8 times 10 to the negative 11. So this Ka is much, much smaller than the first Ka. We're going to call this Ka1 and Ka2 just so we can distinguish them. So the question asking which acid is stronger has to do with which one makes more products or which one goes more to completion, and that's got to be H2CO3 because the Ka is much, much larger. A larger Ka means the reaction is pushed more forward or there are more products compared to reactants. So H2CO3 is stronger, not because it's the first ionization, but because it has the higher Ka value. So that acid is more likely to donate a proton than the HCO3 minus. Let's do the math with this. Okay, so our next question has to do with H2S. So the first thing I'm going to do is check out the values on the chart for H2S and HS minus. I'm not interested in these values at the moment because those would have to do with, I was looking at a base dissociation instead of an acid dissociation. So H2S is 1 times 10 to the negative 7, and HS minus is 1 times 10 to the negative 13. I'm just going to write that here just so I'll have it as a reference. Ka1 and Ka2 for the first and second dissociations. So we're going to find the concentration of every single thing, starting with H2S and water. So H2S is an acid. It will donate a hydrogen to water, which means water will become H3O+. It's only going to donate one acid, so HS minus will stay as HS minus. Now we're going to plug the numbers in, 0.1 molar H2S. And then when it comes to equilibrium, this will lose some amount X and gain X and gain X. So we'll look at the first Ka, and that's going to be H3O plus times HS minus over H2S. And so that's 1 times 10 to the negative 7. Remember, I got that number off the chart. Is equal to x squared over 0.1, assuming that x is negligible. It's probably a good idea to check to make sure x is negligible. And when I solve that, I end up with x is equal to 1 times 10 to the negative 4. If you want to go back and check to make sure it's negligible, divide by 0.1 times 100, and you end up with 0.1%, which is much less than 5%, so your approximation was valid. Take that off for the moment, though. Okay, so x is equal to 1 times 10 to the negative 4. Now in the equation, we said that x was equal to H3O plus, and x is also equal to HS minus. X is equal to H3O plus and HS minus. So that 1 times 10 to the negative 4 is both of those entities. Now let's look at the second dissociation. This time we're starting with the HS minus and water. And we're going to make H3O plus and S minus 2. So we just said that x was equal to 1 times 10 to the negative 4. And x was equal to HS minus and H3O plus. So that's how much of those two things we have at the beginning, initially, before this reaction starts. Then we'll minus x, and also make the approximation that x is negligible. So now we're looking at Ka2. So Ka2, which I got off of my chart, is 1 times 10 to the negative 13. And this is going to be equal to 1 times 10 to the negative 4 times x divided by 1 times 10 to the negative 4. And hopefully you're seeing that you're going to have these guys cancel. So you end up with, wait, hold on, let's try that nicer. You end up with this is equal to x. 1 times 10 to the negative 13 is x. And in this case, x is equal to the concentration of S minus 2. So when it's asking for H2S, H2S was the original 0.1 molar. Minus 1 times 10 to the negative 4, but since that was such a small percent, it shouldn't really matter. H3O plus was 1 times 10 to the negative 4. And if you want to check the percent ionization, 1 times 10 to the negative 13 divided by 1 times 10 to the negative 4 times 100, 1 times 10 to the negative 7%. That's 0.0000001%, which is significantly smaller than 5%, so that contribution of x is negligible. All right, then HS minus is also 1 times 10 to the negative 4. And then S minus 2 is what we just found, 1 times 10 to the negative 13. So that's your polyprotic acid. Okay, for our next problem, we're looking at H3PO4. So the first thing I'm going to do is just check out my chart. H3PO4 with Ka1. H2PO4 minus with Ka2, and HPO4 minus 2 with Ka3. So just know that that chart is there and know that I'm getting those numbers from somewhere. So now, try this problem on your own. See if you can work it all out and get the concentrations of everything, including the pH. Pause your video now. So hopefully you did that. We got H3PO4. This is our first ionization, and this time I'm going to do it without water, just because I want you to see that it can be with or without water. The H plus and H3O plus are interchangeable. So H3PO4 makes H plus and H2PO4 minus. This is a weak acid. And it starts at 5 molar, minus X plus X plus X. Now your equilibrium expression for Ka1 is H plus times H2PO4 minus over H3PO4. And on the chart that was 7.5 times 10 to the negative 3 is equal to x squared divided by, make this approximation, 5. So I'll multiply by 5 and then take the square root. I end up with x is equal to 0.194. And then based on this equation, that's going to be H plus and H2PO4 minus. So now we need our second ionization. We're going to start with the second acid, H2PO4 minus. And I have H plus because it's going to lose one hydrogen, and HPO4 minus 2. So we already said that H plus is 0.194. And H2PO4 minus is 0.194. When it comes to equilibrium, this will minus x plus x plus x. This is approximately 0.194. This is approximately 0.194. So we have Ka2 H plus times HPO4 minus 2 divided by H2PO4 minus, based on your chart, 6.2 times 10 to the negative 8 is equal to 0.194 times x divided by 0.194. And then notice that these guys cancel, so that equals x. And this time, x is equal to HPO4 minus 2 only. Now, I'm going to go into the third ionization equation, so let me clear my board. For the third ionization equation, we're starting with HPO4 minus 2. And this is going to lose the last hydrogen that exists, so that'll be H plus and PO4 minus 3. We just said that HPO4 minus 2 was 6.2 times 10 to the negative 8. Now what's funny, or what you might make sure you want to pay attention to, is that we had already found H plus earlier, 0.194. And in the previous equation. And then the x, again, is going to be negligible from the previous equation, so we have still 0.194. Now this reaction is also going to come to equilibrium, minus x plus x plus x. So this is equal to approximately 6.2 times 10 to the negative 8. And this is equal to approximately 0.194. And then the other guy's x. So now we have Ka3 H plus times PO4 minus 3 divided by HPO4 minus 2. And that Ka3 that I got off the chart was 1.7 times 10 to the negative 12, which is 0.194 times x divided by 6.2 times 10 to the negative 8, so that x is equal to 5.43 times 10 to the negative 19. And then in this case, x is equal to PO4 minus 3 only. So now the question is, what are the concentrations of everything? So let's go back and look at the work we had. H3PO4 was approximately 5. If you would like to subtract that first x, subtract that 0.194, you can say 4.81. But if you leave it as 5, that's totally fine. H2PO4 minus and H plus were both 0.194. HPO4 minus 2, that was from my previous problem, was 6.2 times 10 to the negative 8. And then PO4 minus 3, which we just now found, was 5.43 times 10 to the negative 19. The other question that's asking is calculate the pH. So pH has to do with the H plus. pH is equal to negative log of the H plus, 0.194. And that's going to be 0.713. And there you go. And that's your polyprotic acid problem with phosphoric acid. Our next problem has to do with sulfuric acid. And notice that H2SO4 is not on this list. H2SO4 does not exist because H2SO4 is strong. So it's not going to be on this list because it doesn't have a Ka. Actually, its Ka is so large it's approaching infinity. But I do see HSO4 minus, which does have a Ka. And that'll be about it. So let's use that Ka for our next problem. First thing we're going to do is write the reaction. H2SO4. This time I'll add water. I'm trying to alternate when I add water and when I don't, just so you can see them both ways. If you did this reaction without adding water, that's totally fine. Now this is a 1 arrow because this is a strong. So this is 1 molar. But the thing is, it's 1 arrow because it's strong, which means that all of that H2SO4 will turn into H3O plus and HSO4 minus. All of it will. Not just a little bit, but all of it will. So I don't have to write out a Ka expression because there is no equilibrium because this reaction goes to completion. H3O plus is 1 and HSO4 minus is 1. So I can just move straight on to the next equation. HSO4 minus plus water. This time we have a weak reaction. H3O plus and SO4 minus 2. So I'm going to start with H3O plus and HSO4 minus, both of them as 1, because I got that from my previous problem. Now I can minus x, approximately equal to 1, approximately equal to 1. My Ka value, H3O plus times SO4 minus 2 divided by HSO4 minus. So we found that number on the chart, that was 0.012, is equal to 1 times x divided by 1, which is x, which is SO4 minus 2. If you want to check whether or not x is negligible, just to make sure we did it right, we'll have the thing that we found out for x, which is 0.012, divided by the original, which was 1, times 100, gives you 1.2%, which is less than 5%, which means x is negligible, our approximation was valid, and H3O plus really is 1. So the pH is equal to negative log of 1, which is 0. A really, really low pH, which means a really, really strong acid. The next problem looks very, very similar, except that now the concentration for that H2SO4 is a lot smaller than it was before. The math works out virtually the same, except you have a much lower concentration. So we'll have H2SO4 plus water makes H3O plus HSO4 minus. Since this is a strong acid, all of that 0.01 will turn into H3O plus and HSO4 minus. Next equation, HSO4 minus and water. This is a weak reaction. H3O plus and SO4 minus 2. These guys both start at 0.01 minus x plus x plus x. So we'll be writing the Ka. Notice that every time I write the Ka, I write out the expression, like what's going to be included in it. It's a really good idea. So the Ka was 0.012. is equal to 0.01 times x divided by 0.01. So x is equal to 0.12. If you're going to check the percent ionization, the 0.12 that we found divided by the original times 100, 120%, which is totally not okay. That is way more than 5, which means the approximation is not valid, which means erase that. 120%, way more than 5. Also erase this, because I cannot say that that's approximately equal to 0.01. And start over again without that approximation in place. 0.01 plus x times x divided by 0.01 minus x. Distribute, cross multiply, quadratic equation. I end up with 1.2 times 10 to the negative 4 minus 0.012x equals 0.01x plus x squared. Putting all the like terms on the same side, 0 is equal to x squared plus 0.022x minus 1.2 times 10 to the negative 4. So that A is equal to 1, B is equal to positive 0.022, and C is equal to negative 1.2 times 10 to the negative 4. X is equal to negative B plus or minus the square root of B squared minus 4AC all over 2A. So we'll have to plug all this into the quadratic equation. And I end up with, please pause now and check to make sure you're going to get the same math as I do, and I end up with x is equal to 0.0045 or negative 0.0265. A negative number will not work, so this is my x. So if that's my x, I'm still looking for pH, so I'm going to take that x and add it into my H plus because the x is not negligible. So my H3O plus is 0.01 plus 0.0045, which is equal to 0.0145. So pH, the negative log of 0.0145 is equal to 1.84. And that's my pH. So when you have a sufficiently concentrated acid, polyprotic acid, then the X will be negligible. But when your acid is relatively dilute, like 0.01 molar instead of 1 molar, then the X might not be negligible. So it's a good idea to go back and check to make sure your approximation was valid. All right, well that was polyprotic acids. Join me again next time for the hydrolysis of salts.